Hello, everybody. This video addresses some of the questions that y'all asked during the last two sections in Chapter 7. So problems 120, 121, 123, and 124 were some of the frequently asked questions. So problem 120, let's see, it says the amount of water evaporating from a conical container varies directly. So that means we have direct variation. So y equals kx is the equation we use when y varies directly as x. And so in this case, we're going to have the rate of evaporation is equal to some constant. It says varies directly with the exposed surface area. And so that's the area of the circle. We'll call that A. So E equals some constant times A. And let's see. The height of the cone is 10 meters. When the height of the water is 5 meters, as is shown in the diagram, the radius of the circle is 3. So at this point, the water is evaporating at 0.2. So our evaporation rate is 0.2, some constant times the area. When the radius is 3, the area is going to be 9 pi. So that means K is equal to 0.2 divided by 9 pi, which is about 0.00707. So that is our constant, and so now we know that E is equal to 0.00707 times whatever the current area is. How fast is the water evaporating when the container is full? So when the container is full, we're going to get a similar triangle up here with the height being 10, and we don't know the radius at that point when it's full, so we'll say small height 5 over small radius 3 equals big height 10 over small radius, or over big radius r. So we have height over radius equals height over radius. So that gives us 5r equals 30. So r equals 6. So that makes sense. When the height is twice as tall, the radius is twice as large. So the radius would be 6, which means our area at that time would be 36 pi. And so using this equation, we can get E equals 0.00707 times the area, which at that time is 36 pi. And so our rate of evaporation at that time when it's full is 0.00707 times 36 pi, and that is 0.8. So 0.8, and the units were originally liters per hour, so this is also going to be liters per hour. How fast is the water evaporating when it is half full? So half full would be not when it's half the height. So we would need to calculate the volume and figure out what is the height when it's half full. So the volume full would be 1/3 pi times 6 squared times 10. So we figured out that when it's full, the height is 10 and the radius is 6. And so that is 1 divided by 3 times pi times 36 times 10. So I got about 376.99. So the volume when it's half full would be half of that. So that's 188.4956. And now we just need to find the radius at that time and the height. And so according to this proportion that we had, the ratio of height over radius is always 5/3. And so that means our height is always 5/3 the radius. If you multiply both sides by r, height equals 5/3 radius. And so over here we have 1/3 pi r squared h, but h is 5/3 r, equals 188.4956. And so that is 5/9 pi r cubed equals 188.4950. So if you solve for r, you would multiply by 9/5 and divide by pi. So 188 times 9 divided by 5, and then also divided by pi. Gives us 108, and then take the cube root of that. So 108 to the 1/3 power tells us our radius at that time is about 4.7622. And so our area of our circle at that time is pi times 4.7622 squared, which is about 71.25. And so then we can again use this equation and get E at that time is 0.00707 times 71.25, and that is about 0.5. So E is about 0.5. And the units again are liters per hour. Okay, so that completes problem 20, or 120. And then another frequently asked problem was 121. So we're going to solve for x. So let's see, we have 8 times 4 to the x equals, here we would have 1/2x raised to the 1/3 power, and that is 1/2 to the x over 3. So we have 8 times 4 to the x equals 2 to the negative x over 3. And we should try to get all the x's together on the same side, so I'm going to divide by 2, or actually, let's go back to this step, and then I'm going to multiply both sides by 2 times x over 3, 2 raised to the x over 3, and so that's going to give us 1 on this side, equals, let's see, we have 2 to the x over 3. I'm going to write 4 to the x as 2 to the 2x, because 2 squared is 4, times 8. And now I have 2 raised to the x over 3 plus 2x. So 1/3 plus 6/3 is 7/3 x. And then I'm going to divide both sides by 8. So now I have 1/8, which is 1/8 is 2 to the negative 3rd power. And so now we can say that 7/3 x equals negative 3. And so then x equals negative 9/7. Problem B, to get rid of the exponent of 5/6, I'm going to raise that to a power of 6/5. So 32 raised to a power of 6/5. Now I have 3x plus 8, because this all turns into 1, equals, let's see, if we take the 1/5 the root of 32, that's 2, and then 2 raised to the 6th power is 64. And so now we have 3x equals 56, and x equals 56 over 3, or about 18.67. Okay, and then the last problem, let's see, we're going to have to use a logarithm to get the x out of there. So we could say, if we write this, if we take log base 6 of both sides, you could actually do any log, but I'll do log base 6. And so then if we bring the x minus 1 to the front, that's log base 6 of 6, which is 1. And then log base 6 of 3. So then x would equal 1. I'm adding 1 to both sides. So then I get 1 plus log base 6 of 3. And so if you do that on your calculator, log base 6 of 3 is about 0.613. And so that's 1.613. Okay, and then problem 123. We're given this height function. How long does it take for the boulder to hit the ground? So that would be when the height is 0. So we solve the equation, negative 16t squared plus 124 equals 0. And so that would be negative 16t to the 4th equals negative 124. Divide both sides by negative 16. You get 7.75. T to the, that should be second power. T to the second power equals 7.75. And then take the square root to get t. So t equals the square root of 7.75. That's about 2.78 seconds. So that's about how long it takes to reach the ground. That's part A. Part B, what is the average rate of change of the boulder's height over its entire fall? So average rate of change is going to be f of 2.78 minus f of 0 over 2.78 minus 0. So the height at 2.78, we know the height there is 0. The initial height is 124. 2.78 minus 0. So we have negative 124 divided by 2.78. That is negative 44.6. And the units for that are in feet per second. Okay, so that's part B. Part C, what is the instantaneous rate of change of the boulder's height at t equals 1.392 seconds? So that is going to be instantaneous rate of change is going to be the limit as h approaches 0 of the height at 3.392 plus h. It's unfortunate that we used the same letter there. I'm going to just call this f, and we'll say that this height function is f of t. So we have 1.392 plus h minus f of 1.392 over h. That's using our instantaneous rate of change limit. And so that is going to be, since they're giving us decimal values for this, we just want to probably plug in a very, very small number for h. So this is, I'm going to say this is approximately, if we put in, I'm going to say h is 0.0001. And so that's going to be f of 1.3921 minus f of 1.392 over 0.0001. Let's see what that gives us. So after typing that into my calculator, I got negative 44.5456. And the part D, what is the significance of this result? If we'd used a little bit more decimal accuracy on part A and B, I think we're supposed to get the same. This is in feet per second also. We're supposed to get the same value here. So that's the significance of 1.392 seconds, is that that is the time when the instantaneous rate of change is the same as the average rate of change. So remember, we have if we graphed the height of the object, it starts at 124 and it lands at 0 after we said about 2.78 seconds. And so this is the average rate of change, the slope of this secant line from start to end. We said is about negative 44.6. And so there's a time when the instantaneous rate of change, which is the slope of the tangent line, is parallel to the slope of the secant line. And so when those two slopes are the same, that happens at exactly 1.392 seconds for this problem. So that's when the instantaneous rate of change, which is the slope of the tangent, is equal to the slope of the secant. And so average rate of change is the slope of the secant. Instantaneous rate of change is the slope of the tangent. And at that time, 1.392 seconds, it's exactly the same. Okay, so the last problem we have is a big one. That's problem 124. And so we have this diagram, and a man 6 feet tall is walking at a rate of 4 feet per second directly away from a light that is 10 feet above the ground. So we know this is 10. And we would have some similar triangles there. We know the man is 6 feet tall. And so we can say, by similar triangles, 6 over s, that's height over base, is equal to 10 over x plus s. And so that's going to be true no matter where he is. Part A, make a prediction. As the man walks away from the light, is the length of his shadow increasing, constant, or decreasing? So there's not really any wrong answer for that. You're just making a guess of what you think is going to happen. Part B, how long is the man's shadow when he is 10 feet away from the light? And so that's when x is 10. So if we take this equation, part B is going to be 6 over s equals 10 over 10 plus s. And so then if you cross multiply, you get 10s equals 60 plus 6s. That gives you 4s equals 60. So s equals 15. So at that time, the shadow length is 15. If the man currently casts a shadow that is 12.5 feet long, how far is he from the light? So we put in s equals 12.5. So this was part B. So for part C, we're going to say s equals 12.5. 6 over 12.5 equals 10 over x plus 12.5. And then again, cross multiply, we get 125 equals 6x plus 6 times 12.5 is 75. So then we get 50 equals 6x. So x equals 50 divided by 6. And that is about 8.33. So his shadow, for part C, his shadow is longer. No, sorry, for part C, his shadow is shorter. So when he's closer to the light, his shadow is shorter than it is when he's further. So that means his shadow is growing as he walks away. Okay, part E, write an equation to calculate the length of the man's shadow in relation to his distance from the light. And so that would mean taking this proportion and solving for x. Write an equation to calculate the length of the man's shadow in relation to, so we can solve for x or s actually. And so if you cross multiply here, we get 6x plus 6s equals 10s. So then 6x equals 4s, and so you could then say x is equal to 2/3 s, or s equals 3/2 x. So either way, you can get his distance as a function of the shadow length, or you can get his shadow length as a function of the distance. And so that's part E. And then part F, calculate the average rate of change of the man's shadow when he is 3 feet to 5 feet from the light. So average rate of change is going to be his shadow length. So we're going to do shadow at 5 minus shadow at 3 over 5 minus 3. So his shadow at 5, it's going to be 3/2 times 5. So 1.5 times 5 is 7.5. So we have 7.5 minus his shadow at 3 is 4.5 over 2. And so that is 3 divided by 2 is 1.5. So the average rate of change is 1.5, and that's going to be in feet of shadow per feet of distance. So feet over feet. So we just get 1.5. And then part G, how does your prediction in part A relate to your answer in part F? So the average rate of change is positive, which means it's growing. If the average rate of change, not only is it positive, but it's bigger than 1. And so if the shadow was decreasing, then our average rate of change would have been negative. So since our average rate of change is positive, that tells us that the shadow is growing, which matches our answer for part D. And then part H, how does the fact that the man is walking at a rate of 4 feet per second apply to this situation? If you have not already done so, express your answer to part F using delta notation, then evaluate this equation using the rate of 4 feet per second for the rate of change of the shadow. So the change in S related to the change in the distance, we said is 3/2. So if the change in x is 4, the change in s is 6. And so that tells us our shadow is growing at 6 feet per second. Because this was change in x is 4 feet per second. And so this is 6 feet per second. Okay, so that completes those frequently asked questions. Have a great day.